Okay, so after some little problems concerning network, the internet network, okay, I am able to start with some delay the class number 4 of probability and statistics. Okay, so it works, as you have understood. I take this one, I show the slides here, and it will work. I hope so. Okay. So let's start with the part concerning discrete random variables. Be a strange video, but that's the beginning. During the previous session, we have discussed about general definition of random variable. What I have said to you is that in Greek generality, a random variable is something from the universe into R, okay? That is regular, I have said, okay, but forget this notion of regularity because for you everything will be regular. And the advantage of my random variable is that if I start from a probability from A into 0, 1, through my random variable, I will be able to define a new probability that I call the distribution of X. So we have defined Px, okay, such that Px of B is equal to the probability that X belongs to B, for B included in R. And we have proved together that this is a new probability. It fulfills P of the universe is 1. And if I have a sequence of pairwise decision sets, the probability of the union is equal to the sum of the probabilities. Okay? So I have this definition of the distribution. I have also said words concerning the notion of independence for random variable. I have said that in the case where I have two random variables, we say that X and Y are independent if and only if the probability that X belongs to C intersecting the probability that Y belongs to B, C is equal to the product of the associated probability for any B and C included in R. Okay? So it means that for two random variables to be independent, the set of all the associated preimages, in fact, have to be independent in terms of the definition of independence between sets. And taking the example of indicator function, I have proved you that this definition is a real extension of the definition in the case of sets through the notion of indicator function. And the last thing I have defined during the previous session was the distribution function of X that was defined this way, and we have seen together some particular properties for the distribution function. That is to be increasing, okay, to be right continuous, limit in minus infinity 0, limit in plus infinity 1, okay, it characterizes the distribution, and also the fact that if I want to compute the probability that X is strictly greater than A and less than small b, it can be obtained doing the difference of the distribution function between the point B and the point A. Okay? So what we are going to do now, okay, so in the maybe 6 next sessions, we are going to be interested in particular cases of such a situation. The first case will be what we call discrete random variables. And what are discrete random variables? So I will give you the definition just after, but it's very intuitive to understand. What is it? So here, a priori, the set of my possible values is the set of the real numbers. In the case of discrete random variable, we are going to suppose that the set of my possible values will be included in the real numbers, but will be countable. Countable. What is the meaning of countable? It means that it can be finite or infinite, but if it is infinite, my elements can be written as the elements of a sequence. Okay, so I can be infinite in some sense, but not too much infinite. Infinite like the integers are infinite. Okay? So it's this situation we are going to explore in this part, and we have in this part, since we are going to work with an underlying hypothesis of countability, we are going to have some computation easier to do than in the general case. Okay? So you have here exactly what I have said. So if I have a mapping from omega into R, this mapping is discrete if, by what I have defined previously as the range of X, that is just the set of the X W such that W belongs to omega, I want this one to be countable. I am countable. Okay? Since I am countable, we are going to introduce a notation for the elements of the set of the possible values, something that I have called the range during the previous session. Okay? And I will give them a name to these values. Okay? So the set of the possible values will be defined from now on as xi, okay, for I belonging to capital I. And in general, capital I for me will be something that will be finite, for example 0, 1, 2, and in this case I have 3 values, or the integers, or the natural numbers, but something that is countable. Okay? After we are going to see several examples. Huh? Okay, but here you have the general framework. I am discrete if the set of my possible values is countable. I write this set of possible values this way, and in fact, in order to lighten a little the way we are going to write the proof, we are going to suppose, without any restriction, that in fact they are elements of the real numbers. Okay, we are going to be able to order them. Okay, so I suppose that this one is a strictly increasing mapping. So let's take an example. If I have I that is equal to 0, 1, n, okay, it means that my set of possible elements is just x0, x1, xn, and my hypothesis just means that I have x0 that is strictly less than x1 until strictly less than xn. Okay, I order the set of the possible values. Okay? So it means that if I do a picture, you have here xi, and here, for example, xi plus 1. Okay? In this order, and before here, xi minus 1. Okay? So my set of possible values is countable.
Sorry.
Yeah.
But It's included in, and this letter is countability.
No, it's Z.
So it's
Okay, so once again, in the side of the prerequisite, I have introduced special notations for particular sets. You have the real numbers, you have subintervals of R, you have the integers that I call this way, and you have the natural numbers that I define this way. The Z of the natural number. But if you want intuitively, it just means that here you have something that is finite, a finite number of elements as in this case, or a sequence. Okay? It will be the two cases we are going to see together. Okay? Classical sequences.
This is natural numbers, not integers.
Yeah, natural number this one, integers this one.
Okay.
Okay? But sometimes, okay, it's to take into account the fact that I can also have negative values, let's say, okay? But typically, in general, okay, we will be in the finite case or in the case of this one, okay? And we are going to suppose nothing more, but being in this setting, okay, will have several consequences. Why I will have several consequences? Because if I come back to the definition of what is a probability of the universe is 1, and if I have a sequence of pairwise division set, the probability of the union is equal to the sum of the probabilities. So in the definition of the probability itself, of the probability P itself, you have in the definition something that is related to countability, to be countable. And in fact, it will match in a good way with discrete random variables that are also intrinsically related to the notion of countability. Okay? So we are going to be able to do some operations that we won't be able to do in the general case. That is the case where I take values, okay, in a set that is not countable because I am countable. Okay? Typically, you have the formula in red on the slide here. So if I come back to what I have reminded at the beginning here, in the general case, I have defined the distribution of a random variable this way. It means that if you want to know Px, you need to know all these probabilities for any subset of the real numbers. Okay? So it means that a priori you have a lot of work to do. Okay? You have to do and to compute this for any b, arbitrary b. Okay? In my particular situation, in fact, it will be a little bit simpler. Why it will be a little bit simpler? I erase this one here. But it will be a little bit simpler because if I am interested in x belongs to b. Okay? So what is this one? It's the set of the W belonging to omega such that xW belongs to B. Okay? But I know that the set of my possible values is equal to this one. Okay? So I can write this set in the following way. It will be a union over I of what? Of the set of the W such that xW is equal to xi, but for the xi that are in B. So the set of the I such that xi belongs to B. Okay? To say that I belong to a set just means that I take the value of one particular element of this set. It's exactly what I have written here. To belongs to means that I am equal to something that is in B. Okay? But what is interesting here is that here I am countable. Here you have a countable union. You have a countable union here. In the case of discrete random variable, you have a countable union. Something that is not true if you don't suppose that capital X is discrete. If capital X take values in the real number without any kind of restriction, in general, this union is not a countable one, okay? Because you may have a finite number of elements in B, okay? But here, I have a union that is countable, and I have also a countable union of sets here that are in fact pairwise disjunct, because it's not possible to take two different values for mapping, okay? So you have here, in fact, a countable family of pairwise disjunct sets, okay? From the definition of a probability, the probability of the union is equal to the sum of the probabilities. And so, if I ask you to compute this one, okay, you obtain the sum on the set of the I such that xi belongs to B of what? Of the probability of this set, that is the probability that x is equal to xi. And what is the consequence of this one? It means that if you know all these terms, you will be able to compute all these probabilities. So whatever complicated is capital B, if you know all these terms, you will be able to compute the associated probability here. But I repeat, it's because I have a countable union. If you are not in the discrete case, and typically in what we are going to do in the next chapter, that is continuous random variable, you will see that for continuous random variable, this reasoning doesn't work, because we can take an infinite number of possible values. Okay? An infinite number of possible values. Is it clear? So, in the discrete case, if you have understood what I have said, if I want to know the distribution of a random variable, it is necessary and sufficient to know these probabilities, and that's why in the slide I give a name to these quantities here. In the discrete case, we call this one, okay, the probability mass function of a discrete random variable. So this one is the probability mass function. The analogous of this one in the continuous case will be the notion of density of a random variable. But in the discrete case, okay, it's what we call the probability mass function. And in other words, okay, to know the distribution of x is equivalent to know the probability mass function in the discrete case. Okay, in the discrete case. Okay, questions? So to compute all these terms, it is sufficient for you to know all these ones. Okay, and it's better to have to do this only, because these events are simple. This one may be very complicated, but whatever. Okay? If I know this one, I will be able to know this one. Okay, so a last remark before to show you classical examples of discrete random variables, okay? And with illustration, okay, in basic real life situations. Just a remark concerning this one. May I erase the right part of the board? We have seen together that for a general random variable, that is, if I am in this situation without supposing anything, okay, we have proved together that the probability that x is less than b, strictly greater than a, is equal to fxb minus fxa. Okay? So I have this one. So in particular, if I apply this one, if I take a equal in the discrete case to xi minus 1 and b equal to xi, I can apply exactly the same formula. That is the probability that x is strictly greater than xi minus 1 less than xi is equal to fx of xi minus fx of xi minus 1. But what happened in my situation? Keep in mind that I have introduced notations for my possible values. So here you have xi minus 1, that is one possible value of capital X, and then I have xi here. And between the two, I have nothing. So what is this set in the discrete case? What is this probability, in other words? What is the probability to be less than this one and to be strictly greater than this one? Knowing that, I don't take values between the two from the definition of a discrete random variable. So what is the probability in our range here? Oh, no. You have only 1 point in this set. It's the set such that x is equal to this one, because you don't take all the other values. So this one is just the probability that x is equal to x. Okay? And so you see that here, the probability mass function may be deduced from the distribution function, and it explains in particular, okay, in the discrete case, why the distribution function characterizes the distribution function of a random variable in the discrete case, because you are able to recover the probability mass function from the distribution function. Okay? So this is the general definition with the relation between, okay, the probability mass function and the distribution function. But of course, I repeat that what I have written on the slide here is true if I am discrete. If you are in other situations, that is in situation where capital X take values, for example, in wall R, it doesn't work. And I will explain how to deal with this kind of random variable in the next chapter. Okay? So discrete means that I take maybe finite or values that may be written as a sequence, let's say. So we are going to see example and to introduce, okay, some classical, let's say, distribution. We are going to see together the uniform distribution, the Bernoulli, the binomial, the geometric, and the Poisson distribution. That will be the 5 distributions for this part of the course. And for most of them, we have already seen together some examples where they naturally occur, okay, in relation with flipping a coin or rolling a dice. Okay? So, if I want to define distributions in the discrete case, what I will have to define, according to this notation, I will have to define the probability mass function simply. Okay, so it's what we are going to do. Okay, so first case, classical distribution, and by classical distribution, I mean some things that you have to know, okay, for the midterm exam typically. Okay, it's the distribution. So, of course, there are other distributions, but the ones that are considered as included in the course are this one. Okay. So, a random variable, capital X, is said to be a uniform random variable on the set x1, x2, xn. So here I am in a situation where I take only n different values. Okay? And what is to be uniform in this situation? Just to say that the probability for capital X to take the value xk is equal to what? So I have a uniform situation, okay, that is comparable when what happens when you roll a dice that is fair. I have n elements in my set. I want them to have the same probability to occur, okay, and so the probability of each of them is equal to 1 over the number of elements, okay? So in a set with n elements, the uniform distribution on this set is the distribution defined by this probability mass function. Okay? P of x1 equal to 1 over n, P of x2 is equal to 1 over n. For the other values, it's equal to 0. Okay? And of course, in this case, I define a probability because I see that if I do the sum of all these terms from k equal to 1 to n, I obtain 1. 1 over n plus 1 over n plus 1 over n times is equal to 1. Okay? So in the case of the uniform distribution here, the probabilities mass function is just given for the element of the set of the possible values, that is the range, equal to 1 over the number of elements. So we have already seen such a situation in previous sessions. Okay? If I roll a fair classical dice, as written in the slides here, what do you obtain? If you consider, okay, so I roll, you roll a fair classical dice, okay? I denote by capital X the number you obtain. Using my notation in the slides here, what is the distribution of X? Okay, the notation is this one, and with this little arrow here, U for uniform, and this one for the set I am interested in. So in the case of rolling a dice, yes, it's a uniform distribution on the set 1, 2, 3, 4, 5, 6. The probability of each number to occur is equal to 1 over 6. Okay? It's the case of a fair dice. So it's uniform on the set 1, 2, 3, 4, 5, 6. Okay? So we have one example of such a situation. What is this? Okay? Questions? So you have to know the definition, and I will use this notation, okay, for the uniform distribution in the discrete case. It's a calligraphic U here in the slide. And the basic situation is rolling a dice. That is fair. Okay? Questions? Okay? So you will see that in the list 3 and 4 of exercises, we are going to handle these classical distributions. Okay? So, the Bernoulli random variable. So I said that the random variable capital X is a Bernoulli random variable. Bernoulli was a French mathematician with parameter P. So P here is a number that is strictly positive, is strictly less than 1. Okay? So I am a Bernoulli of parameter P if, in fact, the probability that X is equal to 1 is equal to P, and the probability that X is equal to 0 is equal to 1 minus P. All the other probabilities being equal to 0. So it is a situation where I take, in fact, two possible values, 0 or 1. Okay? The probability of 1 is P, and so taking the complementary set, the probability of 0, that is the other possible value, is equal to 1 minus the probability to be equal to 1, that is 1 minus P. Okay? So it's what we call a Bernoulli of parameter P. And typically, this kind of distribution may arise in situations where you have only two outcomes. So typically, two examples of this one. Suppose that you flip a coin such that the probability to obtain, let's say, head is equal to P. P following this one. If I denote by X the random variable defined this way, 1 if head, 0 if tail, okay? But typically, X follows a Bernoulli of parameter P. So typically here you consider X, okay, or the event to obtain a head as a success. It's what you want to obtain, and you have X that allow you to know if you obtain the head or not, okay? Flipping the coin. And of course, if you have a fair coin here, you will have a Bernoulli of parameter 1/2. Okay? And just remark that my condition P strictly positive and P strictly less than 1 is just to ensure that I really take the two values. Because if I have P equal to 0, here it implies that the probability to be equal to 0 is equal to 1. So in fact, it's the case where X is always equal to 0, something that doesn't interest me. And in the case where P is equal to 1 here, it's the probability to be equal to 1 that is equal to 1. And I don't want such cases. Okay? So you have one case where the Bernoulli distribution naturally appears. Another example here, what I have written in the bottom of the slide. The case of an indicator function. Why the case of an indicator function? So I remind you once again the definition of what is an indicator function. Something from omega into 0, 1. It is the first link with something that is Bernoulli. I take two values, 0 or 1, and I know that I am equal to 1 if W belongs to A and 0 otherwise. The definition of the indicator function, and if I want to find the distribution of the indicator function, that is a particular random variable, I need to compute the probability that the indicator function is equal to 1 and the probability that the indicator function is equal to 0. What are these probabilities? When I am equal to 1, when I am in A, so the probability that the indicator function is equal to 1 is equal to P of A. Here I have P of A complementary. According to the definition written on the slides, an indicator function follows a Bernoulli of parameter P of A. Okay? An indicator function is a particular case of a random variable distributed according to a Bernoulli distribution. Okay? And once again here, if you do the sum of all the probabilities, you obtain 1 for sure. P plus 1 minus P, that is equal to. Do you have some questions? It's okay? I can pass to the other case. So uniform, Bernoulli, now binomial. Okay. To have this one in mind, okay, first of all, I remind you something that we have already done together and proved by induction during the previous session. During the previous session, we have seen that A plus B to the power n, okay, is equal to the sum from k equal to 0 to n, c n k, a k, b to the power n minus k. And when you work with binomial distribution, it's a relation that you always have to have in mind. Okay, you will see that we are going to use here, but also in other situations, okay, when we deal with this binomial random variable. Okay, so we said in the situation that x follows a binomial, so I have two parameters here, n and p, okay? it's a distribution depending on two parameters, n belonging to, let's say, n star, and p strictly greater than 0, strictly less than 1. And when I am a Bernoulli distribution of parameter n and p, first, my range is 0, 1, 2, 3 until n. So I take values between 0 and n as it is written on the slide here. The set of my possible values is this one, between 0 and n. Okay? And in this situation, I define the following probability mass function as Cnk p to the power k 1 minus p to the power n minus k. So here, okay, it's a little bit more complicated than what we have seen for the Bernoulli or the uniform, okay? For the Bernoulli and the uniform. And here, k belongs to 0n. First question, why it defines here the probability? In other words, why the sum of all these terms from k equal to 0 to n is equal to 1? I use this one. If I do the sum from k equal to 0 to n, p x equal k, I obtain what? The sum from k equal to 0 to n, cnk, p k, 1 minus p to the power n minus k. If I use the Newton formula here, I obtain what I want, taking for A, p, for B, 1 minus p, p plus 1 minus p is equal to 1. I obtain 1. Okay? So the fact that I define this way a probability mass function comes from the Newton formula we have put together by induction. Okay? So this is what we call a binomial random variable. Several remarks concerning this binomial. There is a link between the binomial and the Bernoulli. So that is there a link between the binomial defined this way and the Bernoulli? So if I have x that follows a Bernoulli of parameter p, I have the probability that x is equal to 1 equal to p, probability that x is equal to 0 is equal to 1 minus p. Is there a link between binomial and Bernoulli?
Sort of approximation?
No. Well, it's more than an approximation, okay? It's a sub-case. How to recover from this one what I have written on the board here? Okay. My question here, how to recover from this one? I will answer the other question after. N equal to 1. At first, you can see this directly on the fact that my set of possible values is 0, 1 to n. If I want the same set of possible values, I have to take n equal to 1. And if I take n equal to 1, I see that the Bernoulli of parameter p is equal to a binomial of parameter 1p. The Bernoulli of parameter p is equal to a binomial of parameter 1p. Okay? So this is a kind of generalization of what I have in mind. Now two remarks. The first one, okay, where this distribution may appear naturally, let's say in real life problems, okay? So just let me to give you a particular example for such distribution to occur. And in fact, it's something that we have already seen together. We are going to flip an unfair coin n times, writing the probability to obtain head equal to p, the probability to obtain tail equal to 1 minus p, and we are interested in counting the number of heads. Okay? I count the number of heads I obtain, flipping n times the same coin that is unfair. Okay? And I said that in this situation, if I denote by capital X the number of heads you obtain, I have exactly a binomial distribution. And more generally, because what is flipping a coin is just something that have two possibilities to occur, here head and tail, but you can change head and tail by everything you have in mind, okay? So if you have a random experiment with two possible outcomes, okay, let's write the first one a success and the second one a failure. If you repeat this n times, and if you count the number of successes, you will obtain a binomial distribution. Okay? So why I have this? So let's start with a very particular case. I take just, okay, n equal to 3 and p, okay? Just mean that I flip my coin 3 times, okay? And I am interested, for example, to, so x, the number of head I obtain, what is the probability that x, let's say, is equal to 0? What is the probability that the number of head is equal to 0? No. When you flip a coin 3 times, it's possible to have, okay, 0 head. Okay? What is this probability? Not P. P is the probability to obtain head. I want 0 heads when I flip 3 times the coin. What is the drawing I have to obtain? It's a drawing where all the elements are tails. So tails on the first, and tails on the second, and tails on the third. The probability to be equal to tail is 1 minus p. So what I obtain, when I flip a coin several times, it's something that is, one drawing is independent from the other. So what is the value here? Not 3 times, no. 1 minus p to the power 3. I obtain tail on the first, and tail on the second, and tail on the third. It's multiplication, not sum. Huh? It's not or, it's and. So I can write it this way. It's the probability to obtain tail on the first, tail on the second, and tail on the third. It is 1 minus p to the power 3. What is the probability that x is equal to 1? The same? No.
1 minus p, where is times p? It's 3 power of p.
So, it's a basic example, so I am able to describe everything explicitly, okay? So, when I say that x is equal to 1, okay, I can write it this way. It means that I obtain only one head. This head can be in the first running, the second one, or the third. So I have this one, it is head 1, tail 2, tail 3, okay? union tail 1, head 2, tail 3, union T1, T2, head 3. Okay? It's the three possibilities to obtain a single head. Okay? Here, of course, I have disjoint case, so the probability of the disjoint union is equal to the sum of the probability. And what is the probability for each one to occur? But I need to obtain, in fact, two tail and one head. The probability of head is P, probability of tail is 1 minus P, so I have P times 1 minus P squared, and 3 times, because I have these three events to compute. So 3 times P, 1 minus P squared. So if you have understood, for x equal to 2, I have 2 heads, okay? So 2 heads means in fact 1 tail, and in fact it's exactly the same one, changing P into 1 minus P, okay? But let's write it at the beginning so I can write it this way. So I have tail 1, tail 2, head 3, so it's equal to 2, so it's 2 heads, excuse me. So I have this one, I have head 1, tail 2, 3, union, head 1, head 2, tail 3. The probability of each of them is equal to what? I have 1 tail and 2 heads. Probability of head P, probability of tail 1 minus P, but I do this for 2. So I have P times 1 minus P, I have 1 minus P times P squared, and I do the probability of the union of 3 sets that have the same probability of occur and that are disjoint, so I obtain 3 of what? Of 1 minus P squared. And the last, what is the probability that I obtain 3 head? I have only one drawing that allows to obtain this, that is head, probability P to the power 3. And you see that in this situation, in fact, if you take n equal to 3 in my definition, it's exactly what you obtain, because C1, 3 is equal to 3, and C2, 3 is also equal to 3. So what I obtain here is just what I obtain in my definition for n equal to 3. And in fact, what I have done in this basic example may be done exactly in the same way for general n. It's not more complicated, it's exactly the same thing. The only thing you have to have in mind is that, in fact, why I have 3 possibilities here and why I have 3 possibilities. But because if I want one head, it means that I have to choose what is the place, let's say, of the head. Since I have 3 possible places when I flip the coin 3 times, okay, I have to choose one place among 3, and I do this, okay, without order and without repetition. So it is C1, 3. Here, I have to choose 2 heads among possible 3, and to do this, it's to choose 2 elements among 3 without order and without repetition, what I have called C2, 3, that is equal to 3. So here you have C1, 3, here you have C2, 3.
I
have the car.
Yeah, sure. So I have a question regarding notation. So during the exam, I have to use this notation with disjoint union process, or would it be sufficient if I would just use the binomial coefficient?
You have to explain.
Okay.
Every time you have to. Okay. So be careful, because okay, when I write to the board, okay, the advantage of a teacher when he he do the course or when he correct exercises is the fact that he can speak. See, I write and I explain. Okay? Unfortunately for you, when you do an exam, it's not possible to speak with me. So I want the explanation on the page. So here, I don't write everything, but I explain. And it's your job to take the notes, okay? Because I have a small board, if I write everything, okay, I will do half of the program, okay? But of course, you have to explain everything, okay? And by to explain, I mean just I want something that will be sufficient for one other student to be and to understand the exercise. It's my criteria, in fact. If I give your solution to another student, if it is okay, it's okay for me. Okay? If it is not, in general, it means that you have expectations that are not okay. That are not. So I have done the job for n equal to 3, but if you have understood, okay, for a general n, it's exactly the same thing. You have to distinguish cases, okay? And just to keep in mind that the C and K that is involved in the definition of the binomial is just to choose K element among n without order and without repetition. That is exactly what we do here when we have to choose the place of the head and when we have to choose the place of the two heads among the three flips. Okay? So binomial appears as repetitions of a random experiment with two outcomes, a success and a failure, and when I want to count the number of success. It's what you need to have in mind, okay, intuitively, to make links between the binomial and, let's say, real-life experiments. Okay? The last result we are going to see concerning the binomial, I have said that a Bernoulli is just a very particular choice of a binomial. What we are going to see now is the fact that any binomial may be defined from Bernoulli random variables. So it's a little exercise we are going to do that is inside the course, okay? May I erase the board?
Okay.
Yeah? Well, I erase this part here. So the statement of my exercise is this one. So it's not an exercise from the list, it's just an exercise from the course, okay? So suppose that you have, suppose that x1, x2, xn are independent Bernoulli of parameter P. So I have n random variables that have a distribution that is a Bernoulli distribution, and I suppose that they are independent. What I want you to prove is that, in fact, x1 plus x2 plus xn, that is the sum of my independent Bernoulli, follows a binomial of parameter n. If you do the sum of n independent Bernoulli of parameter p with the same parameter, you obtain a binomial of parameter n and p. From an intuitive point of view, it's that clear. Because if you have in mind here, what I do flipping the coin, I say that I have defined or see that the binomial appears when I flip a coin several times and count the number of heads. If you define this one, this Bernoulli as, okay, what is x1? x1 is 1 if I obtain head on the first, 0 otherwise. x2 is 1 if I obtain head on the second, 0 otherwise. x3 and so on. When you do the sum, what you do, in fact, you count exactly the number of heads you obtain. Okay? So it's one way to prove using intuitive arguments, okay, that are taken from flipping a coin. Well, it's not the way I will do, because it will be possible to do it by induction, and I want to do another time an induction in the course, okay? So let's prove this one. I repeat that you can prove it using intuitive argument coming from flipping a coin n times, okay? But we are going to do it in another way using typically an induction reasoning. Okay? So I erase this one. Okay, so if I want to do an induction, I have to initialize and I have to prove the heredity. Okay, so here I initialize at n equal to 1, okay, because n belongs to n star in my slide. Okay, n is not 0, and it's something that I have already seen because we have seen together that a Bernoulli of parameter p is a binomial of parameter 1p. So okay, because you can write it this way, a Bernoulli of parameter p is just a binomial of parameter 1p. So for n equal to 1, I have my job. If I have a single random variable, a single x1, of course it follows a b1p because b1p is bp. Okay. So I have initialized my induction. And now I suppose the result true for n minus 1, and my job is to prove it for n. So my induction hypothesis is the fact that x1 plus xn minus 1 follows a b n minus 1 p. Okay? It's my induction hypothesis. If I don't do the sum of the n but of the n minus 1, okay, I have my result. And my job is to deal with x1 plus x2 until xn. Okay? I have an hypothesis concerning the n minus 1 terms of the sum. That is my induction hypothesis. And I want to deduce something about the sum of all of them. So first of all, what is the set of the possible values for this sum here? Each one is a Bernoulli. So for each one, what are the possible values? 0, 1. So if I do the sum of n terms, that may be equal to 0 or 1. What you obtain for the sum as possible values? But the two extreme cases are the case where I obtain all 0, so I obtain 0, and all 1, that is n. So I belong to 0, 1 until n. Unfortunately, because it's exactly my set of definition in the case of the Bernoulli. Okay. So let's see what happens. So if I want to prove that this sum follows a Bernoulli of parameter np, I have to prove that I will compute the probability mass function of this one and prove that it is exactly what I have on the slide. Okay? So I am interested in the probability that x1 plus x2 plus xn is equal to k for k between 0 and n. Okay? So I said that I have cases that are easy to compute. What happened for k equal to 0? What is the probability that the sum is equal to 0? So, all of them have to be equal to 0. If I want the sum to be equal to 0, I don't have the choice because they take values between 0 or 1. So if I want the sum equal to 0, it means that they are all equal to 0. But they are independent, so the probability of the intersection is equal to the product of the probabilities, and the probability of each event is equal to In the case of a Bernoulli, the probability to be equal to 0 is 1 minus p. So using independence and the fact that I have a Bernoulli distribution, I have 1 minus p to the power n. So for k equal to 0, I am able to do the job. And for k equal to 0, if I take this expression for k equal to 0, C0n is equal to 1, p to the power 0 is 1, 1 minus p to the power n minus 0 is equal exactly to 1 minus p to the power n. So this is for k equal to 0. I have done the job for k equal to 0. For k equal to n. For k equal to n, it's exactly the same kind of situation because I have n terms in my sum. I want the sum to be equal to n. It means that I don't have the choice. All of the terms of the sum have to be equal to 1. So it's the same thing like this one, okay, but replacing 0 by 1. I use the independence, the definition of a Bernoulli, and I obtain, in the last case, p to the power n. That is exactly what I obtain here if I take k equal to n, because Cnn is 1, Pn is p to the power n, like this one, and 1 minus p to the power n minus n is equal to 1. Okay? So I do the job for the first and the last. And now, in order to finish, my job will be to do the same for all the intermediate cases here. Okay? So it's what we are going to do. And keep in mind that for the moment, I don't have used my induction hypothesis. Sometimes, okay, we will have to use. Okay? For the moment, what I have written may be done by a direct reasoning, and it's for the other cases, k equal to 1, k equal to 2, and k equal to n minus 1, that I will have to use this induction hypothesis. Okay? So, now, the cases that interest me are the cases k between 1 and n minus 1, because I have done the case k equal to 0 and k equal to n. Okay? And I want to compute using the fact that I know things about the sum of the n minus 1 first term. So what can I do here? What I want to do is to use my induction hypothesis. That is, if it is possible to come back to this sum here, it will be a good way. But if I want to come back to this sum, it means that I have to fix what is the value of xn. Okay? If I know what is the value of xn, it's okay. Xn is equal to 0, so it will be x1 plus x2 plus xn minus 1 equal to k. If xn is equal to 1, it will be x1 plus x2 plus xn minus 1 equal to k minus 1, and I am able, from my induction hypothesis, to compute both terms. Okay? So if you have understood what I have said, what you are going to use as a formula? But I said that I am able to compute everything if xn is equal to 0 or if xn is equal to 1. So typically, I am in a situation where I can use the induction. Yes, I am doing induction. Okay. The reasoning. I have hypothesis, Bernoulli, the beginning. I want to prove binomial. Okay. But what is the argument that will allow me to pass from this sum with n element to this sum with n minus 1 element? I repeat that if I give you the value of xn, you are able to do the computation. Okay? Because if I say you, if xn is equal to 0, you are able to do the computation because you have this hypothesis. If xn is equal to 1, you are able to do the computation because you have this hypothesis. So, I have two situations, xn equal to 0, xn equal to 1, where I am able to do things, and I want to be able to do things every time. what result in the course I can apply? Yeah, the law of total probability. Okay, you have a partition of the universe that is xn equal to 0, xn equal to 1. We are going to apply the law of total probability. So by the law of total probability, knowing the fact that xn take two values, 0 or 1, so the two events xn equal to 0 or xn equal to 1 are a partition of the universe. And why I do this? Because if I fix the last value in the terms of the sums, okay, I will be able to use easily this one. So I write the law of total probability. I write it this way. So first term, given the fact that xn is equal to 0, and I have to multiply by the probability that xn is equal to 0, plus the same thing given xn equal to 1. Once again, on an exam, if you want to use this one, you have to say that xn equal to 0 and xn equal to 1 is a partition of the universe, because xn take only these two possible values. Okay? Okay. So I can continue my computation. I will continue here. So here, if xn is equal to 0, here I can plug xn equal to 0 in my expression. So I obtain the probability that x1 plus xn minus 1 is equal to k, given xn equal to 0, times the probability that xn is equal to 0. Okay? Because I know that xn is equal to 0, so I can remove it here. Xn is equal to 0 in that situation. Plus the probability that x1 plus xn minus 1. So if xn is equal to 1, it means that this term is equal to 1, and so the sum of the n first is equal to k minus 1. Okay? Equal to k minus 1, given xn equal to 1, probability that xn is equal to 1. And I am able to compute everything here. First, so for the moment I repeat what I have used. Concerning, in this computation here, concerning my hypothesis, I have used nothing. I don't choose the fact. See, the only thing that I have used is that xn take two values, 0 or 1. Okay? But I don't have used that they are independent. In the course concerning conditional probability, we have seen together that if two events are independent, let's say A and B, the probability of A given B is equal to the probability of A. Conditional probability and probability coincide in the case where the sets are independent. And I am typically in this situation because I know that xn is independent of all the other random variables. Okay? Xn is independent of all the other random variables. And so I can write this sum this way. Xn minus 1 equal to k. Probability that xn equal to 0 plus probability x1 plus xn minus 1 equal to k minus 1. Probability that xn is equal to 1. And now I am able to compute everything. Why? Because I have an induction hypothesis. I know that the sum of the n minus 1 first one is a binomial of parameter n minus 1 and p. I know that xn is a Bernoulli. So the probability of this one is equal to 1 minus p. The probability of this one is p. And for these two ones, I am able to use the formula in the case where n is equal to n minus 1. So I obtain what? Maybe I will continue here. So now I use my induction hypothesis to say that I have C n minus 1 k p to the power k 1 minus p to the power n minus 1 minus k multiplied by this term that is 1 minus p plus C n minus 1 k minus 1 p to the power k minus 1 1 minus p to the power what? So it is n minus 1 minus k minus 1. So n minus 1 minus k minus 1 and multiplied by p. At the end, if I simplify a little the power, I obtain C n minus 1 k. I have p to the power k. I have 1 minus p to the power what? I have 1 minus p to the power n minus 1 minus k times 1 minus p, so I obtain n minus k plus what? Plus Cn minus 1 k minus 1 p k minus 1 multiplied by p to the power k. 1 minus p to the power n minus 1 minus k minus 1 is 1 minus p to the power n minus k. So it's almost finished. I see that I have in common these two things. So I can put it into factor. And what is the sum of the two here? It's something we have seen together in the exercise 24 of the summer list. Cn minus 1 k plus Cn minus 1 k minus 1 is equal to Cn k. It is the first question of the exercise 24 of the summer list. We have done the job together. So this is equal to Cn k p to the power k 1 minus p to the power n minus k using exercise 24 of the summer list. And of course, I obtain what I want. That is exactly that the probability mass function here is given by what I want. That is exactly this term here. Okay, between 0 and 1. So it's something that we will be able to use to say that I can see a binomial of parameter n and p. I can equivalently see it as the sum of n independent Bernoulli of parameter p. Okay? It's another way to have in mind this distribution. So I had some technical problems at the beginning, so we are going to do a break, but a very little one. Okay? 5 minutes. Okay?